Some of humanity's strongest structures were built without any cement at all. These ancient monuments defy everything we know about modern engineering. The Roman Pantheon still stands with its perfect dome after 2,000 years, while our modern concrete crumbles within decades. This video will reveal how forgotten prehistoric formulas created concrete with nearly infinite strength. How did civilizations without laboratories develop materials that outlast empires? What secret knowledge allowed their buildings to heal their own cracks over centuries? The answers could solve our biggest sustainability crises today. What does it mean to build something truly permanent? Beneath the Pantheon's vast dome, the air itself feels heavy with permanence. This is not the brittle shell of modern concrete. It is a living rock shaped by human hands. For nearly 2,000 years, it has defied earthquakes, invasions, and the slow decay of time without a single major crack. Its secret was not a single ingredient, but a chemical recipe lost for centuries. The Romans mixed lime with a special volcanic ash from the town of Pozzolana. This ash, when combined with water and lime, triggers a slow, powerful reaction. It is a process we now call a pozzolanic reaction, though they knew it only through brilliant, careful observation. This reaction does not just stop when the concrete dries. It continues for centuries, forming tiny, fibrous crystals within the material. Scientists like Marie Jackson discovered these crystals are a rare mineral called aluminous tobermorite. Think of it as the concrete's own immune system. When a tiny crack forms, water seeps in, and this water reactivates the long-dormant chemical process. New crystals grow, filling the fissure and welding the stone back together. The wound heals itself. This is the complete opposite of our modern concrete, which weakens the moment water penetrates its defenses. So why did this miraculous knowledge vanish? The Roman Empire fell, and with it, the organized trade and precise engineering standards needed to source the right volcanic ash and mix it in exact ratios. The recipe was not written in a book that could be burned. It was a living practice, and when the practitioners were gone, the secret slept in the stones for over 1,000 years. While the Pantheon's dome defied the heavens, another Roman creation was performing miracles beneath the waves. Along the coast of Italy, ancient harbor breakwaters rest deep in the Mediterranean, submerged for 2,000 years. They have not just survived the relentless saltwater, they have grown stronger. Modern concrete, by stark contrast, begins to corrode and crumble in seawater within a few decades. The secret lies in a deliberate and brilliant recipe. Roman engineers mixed their lime with a specific volcanic ash, but for these underwater structures, they took a seemingly reckless step. They used seawater itself to mix the concrete. To our modern understanding, this is engineering suicide, as salt accelerates the corrosion of steel rebar and weakens our cement. But for the Romans, it was the final, crucial ingredient. When this saltwater mixture combined with the volcanic ash, it triggered an exceptionally rare chemical process. Over centuries, the saltwater acts as a catalyst, slowly growing intricate, interlocking crystals of minerals like philipsite within the concrete's matrix. Think of it as the stone growing its own skeleton, a reinforcing web that becomes denser and more resilient with each passing century. The seawater does not attack this concrete, it feeds it. How could ancient engineers possibly have discovered such a precise formula without microscopes or chemical labs? They did not have our technology, but they possessed something equally powerful: systematic, long-term observation. They were masters of empirical testing, building small-scale prototypes, observing failures over generations, and meticulously noting which local volcanic materials, when combined with lime and seawater, produced the most durable results. Their greatest laboratory was the coastline itself, and their experiments lasted for lifetimes. This was not a single eureka moment, but a legacy of accumulated knowledge, passed down through guilds of builders who understood the hidden language of stone and sea. This regenerative power within ancient stone is not mere legend, it is a visible chemical fact. While our modern concrete structures are designed to be inert and static, these ancient mixtures were engineered to be alive in a geological sense. The heart of this self-healing miracle lies in a specific, highly reactive form of lime. The Romans did not use just any lime, they used a quicklime that was exceptionally rich in calcium oxide. When this potent lime was slaked with water and mixed with their special volcanic ash, the initial setting was only the beginning of the story. The chemical reaction did not simply stop, it entered a dormant state, with unreacted particles of lime and ash waiting inside the stone matrix for centuries. These tiny, dormant particles are the concrete's emergency repair kit. When the smallest hairline crack forms, allowing rainwater or atmospheric moisture to seep inside, it acts as a trigger. The water wakes up the long-dormant chemical reaction. The remaining quicklime reacts again, and new crystals begin to grow, slowly and deliberately filling the fissure from the inside out. Scientists analyzing these ancient samples have found veins of rare minerals like aluminous tobamorite and philipsite snaking through what were once cracks, proving the material literally healed its own wounds. This is not a metaphor, it is a continuous, low-level chemical process that can last for a millennium. So how could ancient builders, without any understanding of chemistry, have possibly identified the right materials for this incredible effect? They were masters of reading the natural world. They would have observed how certain volcanic soils, when mixed with lime and left in the rain, would harden into a rock-like substance over time. They might have noticed that some local clays or ashes, when used in their mixes, resulted in structures that showed fewer cracks after years of exposure. Their selection process was born from generations of trial and error, of watching how different materials behaved under sun, rain, and sea. They learned to recognize the visual and tactile clues of a reactive volcanic ash, clues we are only now relearning with advanced electron microscopes. This regenerative quality represents perhaps the most valuable secret we have lost. Modern engineers are pouring immense resources into creating self-healing concrete, often by embedding brittle capsules of bacteria or polymers. Yet the Romans achieved a far more elegant and lasting solution simply by understanding the latent power within the earth itself. Their concrete was not just built to last, it was built to endure, to adapt, and to heal. What other profound lessons from the ancient world are we still struggling to reinvent? The Roman builder did not rely on distant factories or global supply chains. His most crucial ingredient, the volcanic ash that gave concrete its eternal strength, came directly from the earth beneath his feet. This localized approach to sourcing materials stands in stark contrast to the environmental cost of modern cement production, which is one of the largest single sources of human-caused carbon emissions on the planet. The ancient method created stone, the modern one creates smoke. The Romans were geological connoisseurs. They did not see all volcanic ash as the same. They specifically sought out deposits from regions like Pozzolana, whose ash contained a unique blend of silica and alumina, the perfect chemical composition to trigger the powerful pozzolanic reaction. They understood that the land itself held different recipes, and they mastered the art of regional adaptation. In central Italy, they used a reddish volcanic ash we now call Pozzolana. In Germany, they adapted their formula to use a local crushed brick dust that offered similar reactive properties. In North Africa, they employed volcanic tuff. Each major construction province developed its own signature mix, perfectly calibrated to the minerals available in its local landscape. This was sustainability born not from ideology, but from sheer necessity and profound observation. How did they create such a sophisticated network without modern transportation? The answer is they did not need one. Their system was inherently decentralized. The knowledge was not in the shipping, but in the seeing. Master builders traveled, observing which local materials produced the hardest, most durable mortar. This empirical knowledge was then passed down through guilds, creating a living map of material performance across the empire. They built an empire of stone by first learning to read the land itself. This ancient model offers a powerful lesson for our age of climate crisis. We expend immense energy to quarry limestone, burn it in colossal kilns at extreme temperatures, and then transport the resulting cement across continents. The Romans, in their wisdom, largely skipped the energy-intensive burning step by using reactive volcanic ash that nature had already pre-cooked in the fires of the earth. They leveraged geological processes that had already happened, rather than replicating them with industrial furnaces. Their greatest strength was not moving mountains, but knowing which ones to use. The true secret of Roman concrete was not just in the recipe, but in the rhythm of its making. On those ancient construction sites, the creation of mortar was a slow, deliberate ritual. Roman engineers understood that the process of slaking lime was not a simple task to be rushed. They would soak chunks of quicklime in water for extended periods, sometimes for many months, to achieve a specific putty-like consistency. This was not idle waiting, it was a critical chemical transformation. The long slaking process ensured the lime reached a state of optimal reactivity, priming it to form a stronger, more durable bond with the volcanic ash. Modern analysis shows this patient method produced a lime putty with incredibly fine, uniform particles, creating a far more homogeneous and resilient final product. Our industrial process, by contrast, often uses quicklime that is slaked for mere hours, sacrificing long-term strength for speed. The mixing itself was an art form described in texts by Vitruvius. Materials were not simply dumped together, they were combined in a strict sequence, often starting with the slaked lime putty, then adding the volcanic ash, and finally incorporating aggregates like fist-sized rocks. This entire procedure could take days for a single batch, with teams of workers tirelessly turning the mixture with shovels to achieve a perfect, uniform blend. They were guided not by digital timers but by sensory cues lost to us today. A master mason would judge the readiness by the feel of the mortar on his hands, its temperature against his skin, and the specific sound it made as it was turned. He knew the exact moment when the chemical marriage between lime and ash had reached its peak, a moment we struggle to identify even with our most advanced sensors. This profound, tactile understanding of material behavior was their true trade secret, passed from master to apprentice through generations of hands-on experience. Our modern attempts to replicate Roman concrete often produce inferior results, not because we lack the ingredients, but because we have lost the rhythm of the dance. We possess the sheet music, but we no longer know how to feel the tempo. What other timeless wisdom is hidden not in what they used, but in how they used it? But the stone itself may hold another secret, one that has all but vanished from the evidence. Beyond the volcanic ash and the patient mixing, ancient texts whisper of more unusual ingredients. Some Roman accounts describe adding animal blood or goat's milk to their mortar. Chinese builders from the same era are recorded as using sticky rice soup. To our modern minds, this sounds like superstition, a dash of folklore in a stone soup recipe. Yet chemical analysis suggests these organic materials may have served a profound and practical purpose. Think of an egg white. When you whisk it, it traps tiny pockets of air, creating a foam. Now imagine that same principle on a microscopic scale within concrete. Researchers theorize that protein-based additives like blood or egg albumin could have acted as natural air entraining agents. As the mixture was churned, these proteins would have created billions of microscopic, resilient bubbles throughout the matrix. This would have dramatically improved the concrete's workability, making it easier to pour and shape, but the real magic happened over the long term. In colder climates, these tiny, dispersed air pockets would have provided room for water to expand when it froze, preventing the internal pressures that cause modern concrete to crack and spoil after repeated winters. It was a form of freeze-thaw resistance engineered 1,000 years before the concept was formally understood. Other organic additions, like certain plant extracts, may have played a different role. Tannins from tree bark or sugars from rice could have acted as natural set retarders, slowing the chemical reaction of the lime. This would have allowed for a more controlled, gradual curing process, enabling builders to work with the material for longer and resulting in a denser, more uniform crystalline structure as it finally hardened. The greatest challenge for modern scientists is that these biological components have long since decomposed, leaving almost no physical trace after 2 millennia. So how did ancient builders possibly discover these effects? Their laboratories were the fields, the kitchens, and the workshops of their day. A mason might have noticed that a batch of mortar mixed with water from a trough where animals were slaughtered was easier to spread. A builder in a cold region could have observed over generations that structures made with a certain additive survived the harsh winters better than others. This was not chemistry in a textbook, but a deep, intuitive understanding of material behavior, born from a lifetime of watching how the natural world interacted with their craft. This organic dimension represents a final, elusive frontier in our understanding. We have spent centuries admiring the stone, but we may have overlooked the ghosts of the living world that helped make it eternal. This geometric genius was built into the very bones of their structures. The Romans did not simply pour their miraculous concrete into any shape they desired. They designed forms that played directly to the material's greatest strength, which is an incredible resistance to being crushed, and cleverly sidestepped its relative weakness, which is a low tolerance for being stretched or bent. The arch, the vault, and the dome are not just beautiful shapes, they are masterpieces of structural logic. In a perfectly shaped arch, the force of gravity is transformed. Instead of creating bending stresses that would pull the material apart, the weight is channeled down through the curve, converting it purely into compressive forces that push the stones or concrete together. The material is being asked to do only what it does best to withstand compression. This is why the Pantheon's dome has stood for millennia. Its perfect hemispherical shape and immense thickness at the base ensure that every part of the structure is in compression, essentially squeezing itself together more tightly under its own weight. Modern reinforced concrete, by contrast, relies on steel bars to handle the tensile or stretching forces. This steel is the system's Achilles heel, the component that eventually rusts and fails, causing the concrete to crack and spoil. The Romans engineered a system where the geometry itself was the reinforcement. They even understood the subtleties of their own designs. Look closely at the coffered, indented panels on the inside of the Pantheon's dome. These are not merely decorative, they strategically reduce the dome's overall weight without sacrificing its structural depth, and they are precisely positioned in areas of lower stress. It is a perfect marriage of form and physical law. How could they possibly calculate these intricate stress distributions without finite element analysis or computer models? Their tools were generations of observation and a profound, intuitive grasp of geometry learned through physical modeling. They built small-scale prototypes, tested arches until they found the ideal proportion of rise to span, and learned through collapsed failures which shapes brought enduring stability. This knowledge was encoded in strict geometric rules and ratios passed down through guilds. A master builder knew that an arch of a certain span needed a specific curvature and thickness, not because he had a mathematical formula, but because his teacher's teacher had shown him the ruins of one that did not. This was an engineering philosophy that worked in harmony with nature's forces rather than fighting them. They even oriented their buildings to account for seasonal sun and wind patterns, reducing thermal stress on the massive stone shells. We now use supercomputers to simulate the very same principles they discovered by building, watching, and learning from the land itself. Their geometric wisdom was a kind of frozen music, a silent intelligence locked in stone that we are only now learning to hear again. The silent stones of ancient Egypt hold a different kind of wisdom from those of Rome. In the dry, scorching heat, Egyptian builders crafted a concrete not from volcanic ash, but from gypsum and lime, a formula that could set quickly and withstand relentless sun without cracking from thermal expansion. Their priority was not healing from water, but resisting its total absence and the daily furnace of the desert. Meanwhile, in the humid, monsoon-drenched climates of Southeast Asia, builders mixed their mortar with organic materials like palm sugar or fruit extracts. These sticky, sugary substances acted as water-resistant barriers, slowing the absorption of moisture and protecting the structures from the constant assault of tropical rains. This was not a single global recipe, but a global library of localized solutions. Each civilization acted as a master chemist for its own specific climate, developing a bespoke material that spoke the language of its local environment. How could they possibly achieve such precision without climate chambers or accelerated aging tests? Their laboratory was time itself, and their data was written in the ruins of their own failures. A community would observe that a temple built with a certain local clay showed severe cracking after just a few rainy seasons, while another, made with a different mix of crushed brick and lime, stood firm for generations. They learned which river sands produced a mortar that crumbled in the frost, and which volcanic aggregates created a wall that could breathe in the humidity. This knowledge was not stored in a database, but in the collective memory of the builders, passed down as oral tradition and refined over centuries of direct sensory observation. They understood the personality of their local climate intimately, and they designed a concrete with a matching personality. This stands in stark contrast to our modern, industrial approach. Today, we produce a universal Portland cement that is shipped and used identically from the arid deserts of Arizona to the frozen tundra of Scandinavia. We then fight against the local environment with energy-intensive heating and cooling systems, sealants, and chemical additives, forcing a one-size-fits-all material to conform to a world of infinite variation. The ancient method was one of harmony, ours is one of resistance. Their climate intelligence offers a powerful blueprint for a more sustainable future. What if, instead of fighting nature with brute force engineering, we once again learn to listen to it, to create buildings that are not just placed in an environment, but are truly born from it? These ancient structures were not built on a deadline. For the master masons of Rome or the pyramid builders of Egypt, construction was a generational endeavor, a patient dialogue with time itself. Modern concrete is mixed poured and expected to reach its full strength within a single month, a process we accelerate with steam and chemical additives. Ancient concrete followed a different clock. Its initial set was merely the opening act of a chemical performance that would continue for centuries. The slow absorption of carbon dioxide from the air, a process called carbonation, worked in concert with those ongoing pozzolanic reactions. Each passing year, each cycle of rain and sun, allowed the material to densify, to knit itself more tightly together, developing a strength and resilience that our accelerated methods can never hope to match. We measure concrete strength in days, they measured it in lifetimes. So what cultural mindset allowed for a building project to outlive its original architect by 100 years? In many of these societies, there was no sharp division between the present and the future. A temple or an aqueduct was not an asset to be completed for immediate profit, but a legacy, a permanent gift to the community and to the gods. The builder understood his work as a single link in a chain that stretched across generations. His pride came from contributing to something eternal, not from meeting a quarterly report. This long-term perspective was built into their very social and economic structures. Projects were often funded by the state or by wealthy patrons seeking immortal honor, creating a stable, continuous investment that could weather political changes. Labor was organized in guilds where knowledge and responsibility were passed from father to son, ensuring that the care and methodology remained consistent over the decades required to complete a cathedral or a colossal dome. There was no concept of a building's lifespan because the building was not meant to have one. This temporal dimension is perhaps the most difficult for us to reclaim. Our entire modern economy is built on speed, on rapid turnover and immediate returns. We pour a foundation in a week and expect the structure to last for 50 years, an exchange that would have been unthinkable to an ancient engineer. Their philosophy was one of deep time, an understanding that true strength cannot be rushed. It must be grown layer by layer, reaction by reaction, year by patient year. What would our world look like if we once again built for the 1,000-year mark? If we accepted that the greatest things we can create are those we ourselves may never see finished? Step inside the Pantheon on a sweltering summer afternoon, and you are met not with oppressive heat but with a profound, earthy coolness. This is no accident of mass. The very composition of the Roman concrete creates a sophisticated thermal system. Its specific density and intricate network of microscopic pores act like a lung for the building. These tiny air pockets trap insulating air, slowing the transfer of heat from the outside in and the inside out. In winter, the massive walls absorb warmth from the weak sun and from the people inside, radiating it back slowly to maintain a stable temperature. In summer, the same thermal mass absorbs the daytime heat, preventing the interior from baking, and then releases it slowly during the cooler night. This passive climate control was engineered directly into the material itself, a stark contrast to our modern reliance on energy-hungry furnaces and air conditioners that fight against our buildings instead of working with them. The ancient builder was not just constructing a shell, he was weaving a blanket of stone. This multifunctional design extended to the realm of sound. Stand in the center of a Roman amphitheater, and even a whisper can be heard clearly in the highest seats. This legendary acoustics was not just a product of the semicircular shape, but of the concrete that formed it. The specific mixture of aggregates, the size of the stones, and the porosity of the mortar all worked together to absorb certain sound frequencies and reflect others, creating a clear, resonant acoustic environment. They were tuning their buildings like musical instruments, using the concrete's composition to shape the behavior of sound waves. How could they possibly calibrate such subtle effects without digital sound meters or acoustic modeling software? Their tools were their own ears and generations of communal feedback. A master builder would listen. He would have a laborer stand on the stage while he moved through the rising tiers of seats, noting where sound dropped or became muddled. Over decades, they learned that a mix with a certain proportion of lightweight pumice aggregate created a different acoustic character than one with heavy river stone. They understood that a slightly rougher wall surface, born from a specific mortar consistency, could diffuse sound more effectively than a perfectly smooth one. This was a science of sensory feedback, where the success of a design was measured by the collective experience of thousands of spectators. Their concrete was not a single-purpose structural material. It was a multi-performance system that provided strength, thermal comfort, and acoustic clarity all at once. This holistic approach stands as a profound critique of our own segmented building science, where structural engineers, mechanical engineers, and acousticians often work in separate silos, adding complex and expensive systems to fix problems that ancient builders solved with a single, brilliantly balanced mixture. What if our buildings could once again be simple, elegant, and multi-skilled, their deepest intelligence hidden not in wires and ducts, but in the very stone they are made from? The ground trembles and modern towers of glass and steel can shatter, but in the same seismic zones, ancient concrete structures have often remained standing for centuries. This is not a matter of luck, it is a testament to a material engineered with a hidden flexibility. The secret lies in the internal architecture of the concrete itself. Roman builders and others in earthquake-prone regions like Greece and Turkey used a carefully graded mixture of aggregates from fine sand up to large, fist-sized rocks. This created a densely interlocking skeleton within the mortar. When seismic waves pass through this composite material, the energy is dissipated along millions of tiny internal boundaries between the different sized stones and the binding paste. The structure can micro-shift and absorb the energy without developing the large, catastrophic cracks that bring down rigid modern buildings. It behaves less like a brittle pane of glass and more like a tough, fibrous piece of wood, able to bend just enough to survive the storm. How could ancient engineers possibly have designed for forces they could not see or measure? Their laboratory was the earthquake itself. After a temblor, master builders would conduct a forensic survey of the damage. They would walk through the rubble, noting which walls had collapsed and, more importantly, which ones had not. They observed that structures with thicker walls and certain proportions often fared better. They might have noticed that a mortar mix using a specific local volcanic ash showed more hairline cracking instead of total failure, a sign it had absorbed the energy. This slow, painful process of observation after each seismic event, over generations, allowed them to empirically refine their formulas. They learned to read the story of the earthquake in the cracks of the surviving stone, incrementally adjusting their recipes to create a concrete that could dance with the earth rather than fight it. This accumulated seismic wisdom, encoded in regional building codes and passed down through guilds, represents a priceless inheritance. We are only now, with advanced material science, beginning to understand the profound intelligence in their seemingly simple mix of rock and ash. A Roman wall does not fade, it ripens. While our modern concrete facades succumb to ugly stains, discoloration, and a slow, dusty decay, these ancient surfaces have developed a rich, elegant patina over the centuries. The sun and rain that scour our buildings have only deepened the character of the old stone. This was no accident of time, it was a deliberate feat of surface engineering. Ancient builders were not just mixing for strength, they were crafting a living skin for their structures. They incorporated finely ground natural minerals directly into their mortar mixes, pigments like ochre for warm reds, volcanic cinders for deep grays, or crushed terracotta for earthy tones. These were not superficial coats of paint, they were integral to the material itself. their color particles locked securely within the slow-forming crystalline matrix of the concrete. As the surface weathered, it did not peel or flake. It wore down infinitesimally slowly, revealing more of the same color beneath, while simultaneously undergoing a subtle chemical transformation. The ongoing pozzolanic reactions at the surface, fueled by centuries of rain and atmospheric moisture, created a thin, hard, glass-like layer of silica-rich minerals. This natural glaze, a patina, protected the interior from further erosion and gave the wall a soft, luminous sheen that no manufactured sealant can replicate. So how did they predict how a color would look after 500 seasons? Their laboratory was the landscape itself. A master builder would observe how a particular local clay, when baked by the sun and washed by the rain for generations, changed its color. He would note which river stones retained their hue and which ones turned dull and powdery. He learned to read the long-term weathering report written on the natural cliffs and rock outcrops around him. If a red volcanic rock on the hillside remained vividly colored for centuries, he knew that same material, crushed and added to his mix, would gift his wall with the same permanence. They were not applying a finish, they were borrowing a piece of the enduring earth and giving it a new form. This stands in stark contrast to our modern approach, where color is often a cheap, thin veneer, a polymer-based paint that breaks down under ultraviolet light and must be reapplied every few years. We fight a constant losing battle against the elements. The ancients, in their wisdom, invited the elements to become co-artists, collaborating with wind and water to create a surface that grows more beautiful and more unique with every passing century. What if our buildings were designed not to resist time, but to bloom within it? The water flowing through a Roman aqueduct was not merely contained, it was transformed. These channels, lined with their special volcanic concrete, acted as slow, deliberate filters. The material's carefully engineered porosity and its reactive chemical nature actively cleansed the water on its long journey from the mountains to the city. As water seeped microscopically through the concrete walls, it interacted with the unreacted lime and volcanic crystals. This process trapped fine sediments and even neutralized certain harmful bacteria, while simultaneously leaching beneficial minerals like calcium into the water supply. The aqueduct was not just a pipe, it was a living, mineralizing organ for the entire city. This stands in stark contrast to our modern water infrastructure, where we rely on impermeable concrete and PVC pipes designed solely to move water as quickly and inertly as possible. We then must build separate, massive, energy-intensive water treatment plants to accomplish what the Romans achieved within the very fabric of their construction. How could ancient engineers possibly have discovered these subtle hydraulic benefits? Their genius lay in integrated observation. A Roman engineer would have noticed that water arriving from a channel lined with a particular mortar mix tasted cleaner and left less sediment in the storage cisterns. He would have seen that such water seemed to keep people healthier than water stored in other types of containers. They were reading the long-term health of their community as direct feedback on their engineering choices. This was not a separate science of hydrology. It was all part of a unified understanding of how their built environment interacted with the natural world and the human body. The great cisterns of Constantinople provide another masterclass in this multifunctional design. These vast underground reservoirs, built with a special waterproof concrete, did more than just hold water. The constant, slow exchange through the concrete walls helped to keep the water cool and aerated, preventing stagnation and algae growth. The infrastructure itself was its own maintenance system. This philosophy represents a sophistication we are only now beginning to appreciate with our modern concepts of biomimicry and integrated design. We typically design each function of a system in isolation, creating networks of single-purpose components that demand constant external energy and intervention. The ancient approach wove these functions together into a single, elegant, and self-regulating whole. Their concrete was not just a barrier against the elements, it was an active participant in the ecosystem of the city, quietly cleaning, cooling, and enhancing the most vital resource of all. What does it mean to build infrastructure that not only lasts for millennia, but actually improves its environment with each passing year? The sheer volume of concrete used to bind the Roman Empire together defies belief. Across the Mediterranean, they poured not thousands, but millions of cubic meters, constructing harbors, aqueducts, and amphitheaters from the deserts of Africa to the misty hills of Britain. This was not a haphazard effort, it was history's first large-scale industrial operation, executed without a single truck or telephone. Their genius was not just in the mix, but in the system. The Romans established a network of standardized production centers, placing them with strategic precision near the sources of key materials. A major harbor project would have its own dedicated mortar production facility, built right next to the local volcanic ash deposit and a reliable source of lime. This localization was their version of a just-in-time supply chain, eliminating the need to transport tons of heavy, bulk materials over vast distances. How did they ensure that a wall in Gaul was built with the same strength and durability as a bridge in Anatolia? They created the ancient world's equivalent of material specification sheets. Imperial engineers documented the ideal properties of Pozzolana ash, the proper methods for slaking lime, and the precise volumetric ratios for mixing. This technical knowledge was compiled into manuals like those written by Vitruvius, and these texts were disseminated to regional governors and master builders, creating a unified standard of practice across thousands of miles. The consistency of the material found in Roman structures from Spain to Syria is a silent testament to the power of this imperial standardization, but manuals alone are not enough. The true secret was the human network. The Roman military often served as the engineering corps, with legions containing specialized troops trained in construction techniques. These soldiers were mobile, disciplined, and could be deployed to major projects, bringing their standardized knowledge with them. Furthermore, guilds of master builders and masons operated across the empire, their apprenticeships ensuring that the tactile, hands-on knowledge of judging a mortar's readiness was passed down through generations without dilution. This created a distributed workforce, a living web of expertise that could maintain quality control on the ground, even when the central authority was weeks of travel away. Their communication system was the well-maintained Roman road itself, carrying not just legions and trade goods, but also teams of engineers and written instructions. What modern business calls distributed manufacturing and quality assurance, they achieved with papyrus, stone tablets, and the unwavering discipline of a system designed to build for eternity. This logistical masterpiece reveals that their greatest strength may not have been in the stones they laid, but in the invisible organizational architecture that allowed them to lay those stones so perfectly for so long across the entire known world. A Roman mason did not merely mix mortar, he performed a sacred alignment with the cosmos. Historical records and later traditions suggest that the creation of concrete was often bound by rituals we would dismiss as superstition. The slaking of lime or the final mixing of a critical batch might be timed to specific lunar phases, conducted under a new moon for foundational work or a full moon for surfaces meant to be seen. Certain mixtures called for the inclusion of materials that held deep spiritual power, ground seashells from a sacred coast, or volcanic ash from a mountain considered the home of a god. These were not arbitrary additions, they were acts of embedding intention and meaning into the very fabric of the stone. The master builder was not just a technician, he was a mediator between the physical world and the spiritual one, and his work was an offering. This cultural framework enforced a level of care and mindfulness that our modern, profit-driven construction schedules simply cannot replicate. When every step of the process is imbued with ritual significance, there is no room for rushing, for cutting corners, or for using substandard materials. The process itself becomes a form of quality control, governed by reverence rather than a checklist. This might explain why our purely technical attempts to recreate Roman concrete sometimes fall short. We can replicate the chemical formula with precision, but we cannot replicate the mindset of the artisan who believed the soul of his community depended on the perfection of his craft. The knowledge was a holistic tapestry woven together from technical skill, environmental observation, and spiritual belief. When the empire collapsed, it was not just the technical manuals that were lost, but the entire cultural ecosystem that gave those manuals their true meaning and ensured they were followed with devout precision. The guilds dissolved, the rituals were forgotten, and the concrete became just a recipe without its soul. We are left analyzing the bare bones of the technology, wondering why the ghost has vanished. What other profound truths about our world have we misplaced because we stopped believing in the magic that helped discover them? A master builder did not measure his materials by weight or volume alone. He measured them by proportion, guided by a hidden mathematical order that governed everything from the curve of an arch to the mix of his mortar. Deep within the composition of ancient concrete, scientists have found evidence of sophisticated mathematical ratios. The blend of different-sized stones, the ratio of volcanic ash to lime, even the amount of water used, often conformed to principles like the golden ratio or the Fibonacci sequence. These are not just abstract numbers, they are the keys to optimal packing density. Imagine filling a jar with a mix of large marbles, smaller pebbles, and fine sand. If you use the right proportions of each, every single space is filled, leaving no wasteful gaps. This is precisely what ancient builders achieved within their concrete. Their specific ratios of large aggregate to small aggregate to binding powder created a material of incredible density and minimal void space. This tightly packed, interlocking skeleton was far stronger and more durable than any haphazard mixture. But the mathematical genius went even deeper. These same ratios also optimized the chemical reactivity of the mixture. The perfect proportion of water to reactive powders ensured that the pozzolanic reaction could proceed fully and uniformly, creating a stronger, more homogeneous crystalline structure throughout the material. The performance was engineered into the numbers. How could cultures across the world, from the Mayans to the Egyptians, possibly converge on these same mathematical patterns without sharing textbooks or calculators? Their laboratory was the geometry of the natural world. They observed the perfect spiral of a nautilus shell, the arrangement of seeds in a sunflower, and the branching of trees. They recognized that these patterns represented a fundamental principle of efficient, strong, and resilient design. By mimicking these natural ratios in their own creations, they were tapping into a deep, universal logic of structural integrity. This numerological wisdom was not written in complex equations, but in simple, repeatable geometric rules and modular systems passed down through apprentice training. A master would teach his student to always use 1 part lime to 2 parts of a specific volcanic ash and 3 parts of a graded mixture of stone. These were easy-to-remember formulas that encoded profound physical truths. Their mathematical approach to material design represents a parallel path to our own modern science, one based on observation of nature's patterns rather than laboratory derivation. We use supercomputers to calculate particle packing models, while they learn to read the same principles in the petals of a flower. This suggests that the ultimate secret of their concrete may not be a list of ingredients, but a way of seeing the world, a philosophy where number, nature, and material were forever intertwined. The hidden perfection of Roman concrete reveals itself only under the gaze of an electron microscope. Modern scientists peer into this ancient stone and find a landscape of breathtaking complexity, a world of interlocking crystals and optimized pores that rivals the most advanced materials we engineer today. The slow, patient curing over centuries was not merely a passage of time, it was a critical manufacturing step. It allowed mineral crystals like aluminous tobermorite to grow to ideal sizes and in perfect orientations, weaving a natural composite material with a toughness that defies replication in our accelerated labs. We observe intricate chemical gradients, where the concentration of reactive elements shifts subtly from the center of a wall to its surface, creating a material that is perfectly tuned for its specific role. This is not a homogeneous blob, it is a masterfully engineered architecture on a nanoscale. The pore structure is a particular marvel. Instead of the large, chaotic voids that weaken modern concrete, the ancient mixture contains a network of billions of tiny, isolated air pockets. These microscopic chambers act like a built-in shock absorption system, dissipating energy from stresses and preventing cracks from propagating. It is a foam of stone, a naturally occurring metamaterial. So how could a Roman mason, working 2,000 years before the invention of the microscope, possibly assess and control these invisible qualities? His tools were profoundly sensory and deeply refined. He judged the quality of his volcanic ash by its feel, rubbing it between his fingers to assess its fineness, knowing that a smooth, almost silky powder indicated the high surface area needed for a strong reaction. He listened to the mix. The specific slurping sound as the shovels turned the mortar gave him clues about its workability and air content. He observed the behavior of a test patch over days and weeks, watching how it cured, how it responded to morning dew and afternoon sun. A master builder learned to read the macro-scale signs of micro-scale perfection. If a trial block showed a fine, uniform set without large cracks, it told him the internal crystal structure was forming correctly. If the surface developed a hard, smooth skin, he knew the chemical gradients at the surface were ideal. Their genius was in correlating these observable, long-term performances with the hidden, internal architecture they created. They developed an intuitive science of material behavior where the proof was not in a lab report, but in a wall that stood unyielding for 1,000 rains. We now use million-dollar microscopes to see what they learned to feel with their hands. This gap between their embodied knowledge and our analytical rediscovery represents one of the most profound puzzles of the ancient world. What other invisible masterpieces did they build simply by learning to listen to the whispers of the earth? An ancient Roman villa does not clash with the Italian hillside, it emerges from it. Its walls are the same color as the local earth, their texture mirroring the nearby stone outcrops. This was no aesthetic accident, it was a deliberate philosophical choice, a form of environmental integration we have largely forgotten. Ancient builders selected their concrete materials not just for strength, but for harmony. They used locally quarried stone for the aggregate and region-specific volcanic ashes, ensuring the finished structure was geologically and visually a continuation of the landscape itself. A building was not placed upon the land, it was grown from it. This principle extended to the very process of aging. While a modern concrete building often stains, discolors, and decays in a way that screams its artificiality, these ancient structures were designed to weather gracefully. Their integral mineral pigments and reactive surfaces interacted with rain, sun, and wind over decades, not to be worn away, but to develop a patina that further bonded them to their site. The building did not fight the elements, it collaborated with them, slowly blending into the environment like a stone in a riverbed, smoothed and settled by the current. What ecological intuition guided this practice? It was a profound, almost biophilic understanding that a structure's longevity depended on its acceptance by the local ecosystem. They observed which natural materials endured in their specific climate and copied them. A dark volcanic stone that resisted lichen in a humid forest became the aggregate for a temple there. A light-colored limestone that reflected the harsh desert sun was crushed for a palace mortar. Their selection process was a deep reading of the land's own durability report. This stands in stark contrast to our modern approach, where we transport identical, sterile gray concrete across continents, forcing a single material to perform in every environment, and then fighting the inevitable dissonance with chemical sealants and constant maintenance. The ancient way was one of dialogue, ours is one of imposition. Their legacy offers a powerful blueprint for a truly sustainable architecture, one where buildings are not just energy efficient, but are inherently, geologically, and spiritually part of the world they inhabit. What would our cities look like if we stopped building on the land and started building with it? The recipe for eternal stone did not simply fade away, it was shattered by the collapse of the world that created it. This was not a single moment of forgetting, but a slow, grinding erasure of an entire ecosystem of knowledge. The Roman Empire provided the perfect conditions for concrete technology to flourish, a stable, interconnected world with state-funded projects, standardized practices, and guilds of highly skilled artisans who passed their tactile wisdom from master to apprentice. This was a living chain of expertise, and when the empire fractured, the links broke one by one. The great building projects ceased, the long-distance trade routes that supplied specialized volcanic ash were severed, and the guilds disbanded as societies turned inward, focused on mere survival. The knowledge did not vanish from a library fire, it evaporated from the hands of the masons who no longer had a reason to mix it. This pattern of technological rise and fall is a haunting theme in human history. The sophisticated water-resistant mortars of the Indus Valley civilization were lost. The durable gypsum plasters of ancient Egypt fell into obscurity. In each case, the same fragile prerequisites were lost: social stability, cultural continuity, and a critical mass of specialized craftsmen working on projects grand enough to require their advanced skills. When a society retreats from complexity, its most sophisticated technologies are often the first casualties. They become too expensive, too organized, and too dependent on a network that no longer exists. Why is it so easy to lose such a powerful advantage? Complex technological knowledge is not a static object you can store in a vault. It is a living process, a dance between theory and practice, and when the music stops, the steps are quickly forgotten. The medieval builders still used lime mortar, but the precise, demanding art of creating the reactive volcanic mixture was gone. He knew how to build a wall, but not how to make it live for 2,000 years. This represents one of humanity's most profound technological regressions. For over a millennium, our buildings became weaker, our structures more temporary. We entered a dark age of masonry, only emerging in the last 2 centuries with the invention of Portland cement, a material we are still struggling to make as resilient as the Roman original. The story of concrete is a stark warning about the fragility of our own technological civilization. Our digital networks, global supply chains, and specialized industries are a modern version of the Roman system. They allow us to create marvels, but they also make our knowledge incredibly vulnerable. What essential wisdom are we one crisis away from losing forever? The silence of the stones asks us what we are doing to make our own knowledge truly permanent. Inside a laboratory, a scientist peers at a screen displaying the ghostly landscape of a 2,000-year-old concrete sample. Magnified thousands of times, it reveals a stunning world of interlocking crystals and labyrinthine pores, a natural masterpiece of material engineering. This is the frontier of modern rediscovery, where advanced tools like X-ray diffraction and electron microscopes are used to deconstruct the very stone that defies our own. The goal is not just to identify ingredients, but to trace the slow, patient chemical pathways that transformed simple lime and ash into a near-eternal stone. We are learning that the Roman recipe was not a static formula, but a guided chemical reaction that unfolded over centuries, a performance we tried to condense into a single month. Each analysis reveals another layer of ancient genius. Scientists can now map the growth of rare minerals like aluminous tobamorite, observing how these fibrous crystals formed slowly around the volcanic glass particles, weaving a reinforcing web that grew stronger with time. They can see the perfect, dense packing of the aggregates, a mathematical marvel that eliminated weak points. Yet for every mystery solved, a new one emerges. How did they achieve such a uniform distribution of reactive particles without modern industrial mixers? How did they intuitively understand the ideal water-to-powder ratio to optimize these long-term reactions? This scientific detective work is proving that ancient builders were materials scientists of the highest order, their empirical methods yielding results we struggle to replicate with all our computational power. The journey to rebuild this lost knowledge is now transforming our own future. The principles uncovered in these ancient samples are inspiring a new generation of green concrete. Scientists are experimenting with engineered synthetic pozzolans, mimicking the chemistry of volcanic ash with industrial byproducts like fly ash. They are exploring ways to encourage self-healing by designing concrete with pockets of unreacted materials, creating a built-in repair system inspired by the Roman model. We are learning to slow down, to design for time rather than fight against it. The quest to understand ancient concrete is no longer just an archaeological curiosity. It is a vital mission to solve our own sustainability crisis. How close are we to pouring a foundation that our descendants will admire 2,000 years from now? The answer is being written not in new formulas, but in the patient, enduring language of the old ones. The true cost of the Pantheon was not measured in coins, but in the invisible architecture of its supply chain. To build with this eternal concrete, an entire economy had to be orchestrated from the ground up, a feat of organization that rivaled the engineering itself. Across the Roman world, a sophisticated network hummed with activity. Quarrymen extracted volcanic ash from the hills of Pozzolana, while lime burners maintained vast kilns that glowed day and night, transforming limestone into the vital quicklime. Teams of laborers processed aggregates, sorting stones by size, while ox carts and barges moved these mountains of raw material to distant construction sites. This was a pre-industrial revolution, all coordinated without a single telephone, spreadsheet, or global shipping company. How did they manage such complexity? Their financial system was built on a foundation of state power and private patronage. Massive public works like aqueducts and harbors were funded directly by the imperial treasury, a bottomless purse fueled by tribute and taxes. At the same time, wealthy citizens competed for prestige by funding temples, baths, and basilicas, their names inscribed for eternity on the very stones they paid for. This created a stable, continuous flow of capital that could fund a project for decades, insulating it from the short-term economic fluctuations that cripple modern construction. The labor was organized with military precision. The Roman legions themselves often served as the engineering corps, their discipline and mobility perfect for large-scale infrastructure projects. Alongside them worked guilds of specialized artisans, the mortar mixers, the stone setters, the master masons. These guilds were the living libraries of technical knowledge, training apprentices through a rigorous, hands-on system that ensured quality control and consistency across generations. A master mason knew his reputation, and his guild's honor depended on the perfection of the wall he built. This was an economy of legacy, not just profit. The organizational genius lay in its decentralization. Instead of a single top-down command, it was a distributed system of expertise. A local foreman knew exactly how many cartloads of sand the riverbed could provide each day. The lime burner knew the precise firing schedule for his kilns. The project architect coordinated these flows, his authority resting on a deep, practical understanding of every step in the process. They achieved monumental scale not by being bigger, but by being more intelligently connected. This ancient model of community-based, resource-aware construction holds profound lessons for our world. We often assume that large-scale building requires massive corporations and complex international finance. Yet here were societies achieving staggering results with localized supply chains and a social contract that valued permanence over quick returns. Their greatest innovation was not in the mix but in the mindset, the collective agreement that some things are worth building together with painstaking care for a future they would never see. A modern laboratory recreation of Roman concrete can meet every chemical specification, yet still lack the soul of the original. Experimental archaeologists have taken this challenge from the page to the field, mixing ancient recipes with reconstructed tools and methods to feel the material come alive in their hands. They are not just analyzing powder, they are building small-scale arches and walls, monitoring these replicas over years to observe how they crack, harden, and interact with rain and sun. This hands-on approach uncovers truths that no microscope can reveal. They learn that the Roman method of dry mixing the volcanic ash and lime before adding water creates a dramatically different workability, a smoother, more cohesive paste that is easier to spread and shape. They feel how the long slaked lime putty gives the mortar a unique plasticity, allowing it to hold its form without sagging. These are the tactile secrets of the master mason, the sensory knowledge that was never written down. The experiments also expose our modern blind spots. When researchers subject their replica samples to accelerated aging tests, they often find that the material behaves differently than predicted. The slow, patient formation of strength-giving crystals cannot be rushed in an oven without compromising the final structure. Our attempts to simulate a century of weathering in a month can create a brittle, artificial version of the real thing, proving that time itself was a crucial, non-negotiable ingredient in the ancient recipe. Each successful replication, each small wall that stands firm after a harsh winter, provides a new piece of the puzzle. It reveals that ancient builders possessed a profound understanding of their material's behavior from the moment it was mixed to centuries after it set. They knew not just the formula but the feel of a perfect batch. So what is the final, elusive gap between our modern recreations and the 2,000-year-old stone? We can replicate the ingredients and the steps, but we are still learning the rhythm, the patience, and the deep, intuitive conversation between the builder and his mix that turned simple earth into eternal stone. These ancient echoes of stone technology resonate across continents and oceans. On the other side of the world from Rome, the Mayans built towering pyramids in the humid jungles of Mesoamerica. Their challenge was not volcanic ash, but the very ground they built upon. They developed a concrete using burned limestone, which they mixed with water and a specific sap-rich tree bark. This organic additive created a mortar that was exceptionally resistant to the constant moisture and heavy rains, a formula perfectly tuned for its rainforest environment. In China, during the same era, engineers of the Qin and Han dynasties were constructing the Great Wall and massive tomb complexes. Their concrete incorporated a surprising ingredient: sticky rice soup. The long carbohydrate chains in the rice acted as a powerful binder, creating a composite material that was not only strong but also highly resistant to water penetration and even earthquake damage. Meanwhile, in ancient India, builders crafted stepwells and temples using surkai, a powder made from crushed, burned bricks. This material, rich in silica and alumina, functioned almost identically to Roman pozzolana, reacting with lime and water to form a durable, hydraulic concrete that could withstand the region's dramatic monsoon cycles. These civilizations were separated by impassable mountains and vast seas, with no possibility of sharing blueprints or recipes. Yet they all arrived at the same fundamental insight, that by combining a source of lime with a reactive silica-rich material, they could unlock a chemical reaction that produced a stone stronger than the sum of its parts. This was not a single secret passed around the globe, but a universal principle of material science, discovered again and again by human ingenuity. The specific ingredients changed with the local landscape. Romans used volcanic ash, Mayans used tree sap, Chinese used rice, and Indians used burned bricks. But the underlying chemical logic remained constant, a hidden rule of nature waiting to be found. What does this global pattern tell us? It suggests that the knowledge to build for eternity is not a lost artifact from one golden age, but a latent potential within the earth itself. When a society reaches a certain scale and ambition, when it seeks to build monuments that will outlast generations, it inevitably begins to experiment with the very stuff of the planet. They learn to read the land, to identify which local materials, when combined with fire and water, can transcend their origins and become something permanent. This convergent evolution of technology points to a profound truth, that the path to infinite strength is written not in one lost scroll, but in the common language of chemistry and stone, a language that every great civilization eventually learned to speak. This ancient wisdom, once fully unlocked, could redefine the very landscape of our future. Imagine bridges that mend their own hairline fractures after a heavy truck rumbles across, or skyscrapers whose concrete bones actively pull carbon dioxide from the polluted city air. These are not scenes from a distant science fiction novel. They are the tangible possibilities emerging from laboratories that are looking backward to move forward. The Roman principle of self-healing, powered by dormant chemical reactions, is being re-engineered for the modern age. Scientists are developing concrete that contains tiny, limestone-producing bacteria or encapsulated mineral precursors. When a crack forms and water seeps in, these internal repair agents are activated, precipitating new calcite crystals to seamlessly seal the wound. This could dramatically reduce the astronomical maintenance costs of our crumbling infrastructure, transforming concrete from a static, decaying material into a dynamic, living system. The environmental impact could be even more profound. Our current method of producing Portland cement is a primary driver of global carbon emissions, but ancient recipes show us another way. By replacing a large portion of cement with industrial byproducts like fly ash, a modern pozzolan, we can create low-carbon concrete that mimics the chemistry of Roman harbor walls. This shift alone could slash the carbon footprint of the entire construction industry, turning a major polluter into a potential carbon sink. Coastal cities, increasingly threatened by rising seas and stronger storms, could be fortified by a new generation of marine concrete. Instead of succumbing to saltwater corrosion in 50 years, our seawalls and piers could be built to gain strength from the ocean, just as the Roman breakwaters did, enduring for centuries and protecting vulnerable communities. This is not merely about copying an old recipe, it is about integrating a forgotten philosophy. The ancient world built with local materials and designed for multi-generational endurance. When we combine that profound insight with our modern tools of nanotechnology and computational modeling, we are not just rediscovering a lost technology, we are initiating a construction revolution. What modern problems, from affordable housing to resilient cities, could we solve if we finally learned to build things that are meant to last forever? A Roman wall was never finished, it was merely entrusted to time. This fundamental shift in perspective is the deepest secret buried within the stones. Ancient builders did not see themselves as conquerors of the natural world, but as collaborators in its slow, powerful cycles. Their concrete was not an inert, man-made substance forced upon the landscape. It was a carefully guided extension of the Earth's own geological processes. They harnessed chemistry that worked on a century-long timescale, designing materials that invited rain, air, and even seawater to participate in a continuous act of strengthening. This philosophy of partnership stands in direct opposition to our modern approach, where material science often seeks to dominate, to create substances so perfectly inert and sealed that they exist in a state of war with their environment. We build walls that fight the weather, while they built walls that conversed with it. The longevity of their structures is a silent, profound critique of our disposable culture. We construct buildings with planned obsolescence, designed to be replaced in 50 years, their value measured in quarterly reports. The ancient world measured value in millennia, building for a future so distant the original architects knew they would only be a memory. This was not a naive idealism. It was a practical recognition that true permanence requires aligning human ambition with the timeless rhythms of nature. What does it mean to build something that is meant to outlive not just you, but your entire civilization? This question forces a radical reconsideration of our relationship with the materials we use. We see resources as something to be extracted and consumed, but the ancients saw them as partners in a grand, enduring project. Their volcanic ash was not just a powder, it was a pre-cooked geological gift. Their patient slaking of lime was not a delay, it was a respectful waiting for a chemical transformation to reach its peak. Every step of their process was an act of listening to the material, of understanding its nature, and working with its inherent properties rather than forcing it to conform to an impatient schedule. The philosophical dimension of this mastery may be its most valuable legacy. Recovering the technical recipe for self-healing concrete would be a monumental achievement, but recovering the mindset that created it would be a revolution. It would mean designing our world not for our own fleeting convenience, but for the permanent enrichment of the generations to come. The stones ask us not just how to build, but why we build at all and for whom. The blueprint for a new kind of engineer is already written in 2,000-year-old stone. Our modern technical education excels at creating specialists, masters of finite element analysis and digital modeling who can calculate stress to the millibar. Yet this hyper-specialization often leaves a critical gap, an intuitive, tactile understanding of how materials live and breathe over centuries. Ancient concrete studies offer a radical curriculum for closing that gap. This is not about replacing computer science with mortar and trowel, but about weaving them together into a richer, more resilient form of knowledge. Imagine a university lab where archaeology students work alongside materials scientists, analyzing the mineral composition of a Roman harbor sample, while architecture students use that data to design a modern, self-healing seawall. The project would not be complete without the historians who trace the social and economic systems that made such construction possible, revealing that a durable material requires a durable society. This is interdisciplinary learning in its truest sense, where the boundaries between fields dissolve in the face of a shared, monumental puzzle. The most powerful lessons would be hands-on. Students could spend a semester patiently slaking lime, mixing it with different local pozzolans, and casting their own small blocks. They would learn to judge the mix not by a digital readout, but by its feel and its sound, developing the sensory skills of a master mason. They would then place these blocks outside to weather, monitoring them over semesters and years, observing first and how some formulas crumble in the frost while others grow a hard, protective skin. This slow, empirical process builds an unshakable intuition for material behavior, a kind of wisdom that no textbook can fully convey. How can we redesign our technical education to include these deep historical lessons? The answer lies in making the past an active partner in innovation. An engineer trained in both nanotechnology and the Roman art of geometric reinforcement would possess a unique creative toolbox, able to draw inspiration from the Pantheon's dome as readily as from the latest polymer research. This educational model does more than produce better engineers. It builds a cultural immune system against the kind of catastrophic knowledge loss that followed Rome's fall. By embedding ancient wisdom into the core of our technical disciplines, we ensure that the secrets of infinite strength are not just studied in ruins, but are actively carried forward, ready to build a world meant to last 1,000 years. Our journey through the stone reveals a truth both humbling and inspiring. The self-healing cracks, the seawater strengthening, the patient rhythms of mixing, these were not primitive tricks. They represent a technology of profound sophistication, one that speaks directly to the sustainability crises we face today. The ancient world solved problems we are still struggling with, from carbon-neutral production to infrastructure that maintains itself. This journey challenges our most basic assumption about progress. Technological advancement is not always a straight line moving forward. Sometimes the most advanced solution is not in a future we have yet to invent, but in a past we have forgotten. The wisdom of these builders offers more than just a better recipe for concrete. It provides a philosophical blueprint for how we might inhabit the earth. They worked in partnership with natural processes, using local materials and designing for time scales that stretched across generations. Their concrete was not imposed upon the landscape, but grown from it. As we look at our own crumbling infrastructure and our planet under strain, their legacy is a call to action. It challenges us to build not for quarterly profits or fleeting political terms, but for a future 1,000 years away. What if the most radical innovation is not a new invention, but an old one rediscovered? The silent, enduring stones ask us to create a world where our grandest structures become gifts to the future, not burdens